In this part, we're going to talk about how to obtain Jacobian matrix from transformation matrices. So before we start, we talk about the Jacobian matrix is actually including two parts. They are JV and J omega. When we are dealing with JV, that's related to linear movement or translation. J omega is related to angular movement. Those two things are different. And because we are using two different type of joints, one is revolute joint, the other one is prismatic joint. JV and J omega are going to be different if you are using different type of joints. So let's talk about those parts. For Revolute joint, we have changes in both angle and position. Because when we are dealing with this type of joints, when this moved, it's change its position from one end to the other. You might have theta or other angular information change from one position to the other. So when you convert everything into angular velocity, you have angular velocity corresponding to the revolute joints. So you need to have that. And because we also know that V equals to omega cross product alpha R, that is something we do in the first slide of this module. So when you have V and you have omega, the JV and J omega needs to be set for those two separate movements. So let's talk about J omega first. For J omega, it's pretty straightforward because we're talking about the angular velocity in terms of x, y, and z. So this one over here is actually omega x, omega y, omega z. You might use psi dot, theta dot, and phi dot in this case, but we can just use omega x, omega y, and omega z. When we are dealing with JV, this time we're talking about linear movement. So we would need to use this part as omega cross product R. But keep in mind, you need to change this one into three components in terms of x direction, y direction, and z direction. We're going to have the formula for this one over here. So the translation actually equals to angular velocity cross product change of position, which is identical to what I just defined over here. But since we're dealing with transformation matrix, how do we define those kind of things? Angular velocity is not difficult to identify because normally we are rotated about z-axis. So when we try to find this kind of things, the angular velocity is actually omega I minus 1. Then we need to find out the length or the change of position. That is going to be my end position minus the one you are interested. So that is going to be position change from one frame to another frame. So when you know the frame, the change of frame in terms of x and y, that is a change of the linear distance. So we multiply this one by omega. That is going to be the angular velocity, linear velocity term, and that is how we get this part over here. And since this one is the delta omega O, it means that that is in change of position, which fulfill the criterion of Jacobian. Keep in mind when we are dealing with Jacobian, it's going to be the difference multiplied by the change of a parameter. So this is going to be satisfy the definition we have earlier. So that is something we need to do for J omega and JV in terms of a Revolute joint. But if we have prismatic joint, then we only have change only in position. Okay? So when we have change only in position, it means that I do not have anything change in terms of angular velocity, which means this part over here is going to be 0, 0, 0. That is because we have prismatic joint. But for linear movement, we're going to use z I minus 1 from your transformation matrix. That is something you need to fill into this matrix. So when you do this part and this part separately, you need to combine them together to synthesize the full column of the Jacobian matrix. Then we can start to use this specific matrix to calculate for everything we want to have and come up with the information of the n effect or the any position you want to have in the system. So before we move on, let's review a little bit about the mathematical requirement. The first thing we want to do is to deal with cross product. When we deal with cross product, I believe you guys know those kind of things when you are dealing with calculus, and in particular, if you have taken dynamics, this is very important part of that course since the movement of rigid bodies. So we have two vectors, A and B. If we want to cross product A and B together, what we want to do is we put something like this. The first row over here are the unit vector of I, J, and K. Then we put A, the three components of A as a second row, the three components of B vector as a third row. You need to follow the direction over here. You cannot interchange the rows of B and A because order matters. You cannot change this one is BX, BY, and BZ, and this one is AX, AY, and AZ. Magnitude-wise, everything is going to be the same, but you're going to attach a negative sign in your answer. So in many cases, you're going to have something like this, a number J, a number I, J, and K, something like that. So when you finish everything like this, you're going to have a equation like this. But when we are dealing with robotics, we hope everything is in terms of vector. So this component over here goes to the first component of this vector, and the second term over here goes to a second component. This one over here goes to the third component. So that is how we represent the cross product of two vectors in robotic systems. And this is something we're going to use in this class. The other thing we want to talk about is if we have transformation matrix, how are we going to deal with those kind of transformation from one frame to another? So based on what we have earlier, if we have joints, this is 0, 1, and 2. So based on the specification, we are going to have a 4x4 matrix from 1 to 2. So we first come up with 0 to 1. Okay, that is also my transformation matrix from 0 to 1. But if I want to do 0 to 2, then I will need to have this one multiplied by this one. Okay, so it will convert from the 0th frame to the second frame. This also implies this is going to be something like this. With that said, if I want to have T03, it is going to be A01, A12, A23. So it also means that my T03 can be represented as T02 multiplied by A23. This is important because when we are dealing with Jacobian matrix derivation, we would need to use those kind of things because we need to get specific components from transformation matrix, and you need to know which frame we're talking about. Based on this frame, we're going to get specifically the column in terms of Z, so that we can synthesize JV and J omega accordingly. We're going to use two examples to explain everything. So next page is going to be something we're going to deal with. So if we have those two equations are actually the formula we are going to use in the rest of this module. If we have a Revolute joint, then the first one, just like what I said, you would need to have the change of position, On minus OI minus N. This one is your destination of your joint, the position where you are interested. And this one is from frame 1 to frame to this current frame, so you can get what your JI is going to be. So depending on how many frame you have, you might need to have individual Jacobian columns accordingly. And this one over here is a Z part, Z column. So we got that is D, that is 1, that's 0. So you have X column, Y column, and Z column. That is going to be this part over here. So over here, if this is Revolute joint, you will need to have the information of those three components over here and over here. And this one over here is used to modify, to obtain the change of position, which means it's angular velocity, linear velocity. And if you have a prismatic joint, then you don't need to worry about that because the angular velocity are always 0, since this one can only perform linear movement. So with that said, you need to put Zi minus 1 as your JV, 0 as your J omega. So those are the important formula or something you need to remember when you start to build your Jacobian matrix. Let's deal with the example. So this is basically the same. We're going to deal with the same thing like what we did earlier, but this time we are not going to get the Jacobian matrix directly from the configuration over here. Instead, we're going to show you guys how to derive all those transformation matrices. Then we use transformation matrices to come up with the Jacobian matrix based on the formula we have on the previous slide. So let's get started. So review how to get transformation matrix. So just recall that when we are dealing with those kind of things, we need to build a table. In this case, certainly we have two links, and we need to find out what is my AI, alpha I, DI, and theta I. Clearly, those two links are generated or moving on XY point, which means alpha is going to be 0. Those two Z are in this direction and they are in parallel, which means the alpha is going to be 0. And since they are on the same point, the depths or the change in Z direction are both 0 as well. Okay, but they are rotating about Z axis, which means theta 1, theta 2. They are both variables over here. And A1, A2, this one is going to be L1, this one is going to be L2. So those are the coefficients that we're going to use. And when we start to get those kind of coefficients, we can get A1, which from frame 0 to frame 1 should be pretty straightforward. It's going to be cosine theta 1, sine theta 1, negative sine theta 1, cosine theta 1, 0, 0, 0, 0, and 1. This is going to be my rotation matrix. And we are not having any linear movement. So the movement over here is only L1, cosine theta 1, L1, sine theta 1, and 0. The fourth row over here is going to be something like this. This is going to be my A1 matrix. And A2 matrix is similar. Basically, you can just copy all the columns over here, all the components over here, because my coordinate becomes something like this. This is something we learned in module 2. So this one over here, we have cosine theta 2, negative sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1, 0, 0, 0. This part over here is going to be L2, cosine theta 2, L2, sine theta 2, 0, 1 over here. Okay, pretty much it's the same as the first transformation matrix, but that is based on this frame. Therefore, this is actually equals to T0 to, let me make sure I didn't give you the wrong information. 0 to 1. And T0 to 2 is going to be A1, A2 together. So we are going to have, if you multiply those two matrices together, you are going to have cosine theta 1 plus theta 2, sine theta 1 plus theta 2, 0. The second one is negative sine theta 1 plus theta 2. This one over here is going to be cosine theta 1 plus theta 2. This one is 0, and this is going to be 0, 0, 1. And over here is going to be L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. And this component over here is going to be L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Okay, and the third component is going to be 0. The fourth row over here is going to be typical ones. And this is going to be my matrix. Okay, so let's rearrange that one over here. T 0 to 2 is going to be A1, A2. Cosine theta 1 plus theta 2, sine theta 1 plus theta 2, 0. Second one over here is negative sine theta 1 plus theta 2, cosine theta 1 plus theta 2, 0. And this one over here is 0, 0, 1. Over here, I have L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Second component over here is L1 sine theta 1 plus L2 sine theta 1 plus theta 2. 0. Of course, there are 3 zeros over here and 1 over here. So this is going to be my transformation matrix. Now, we will need to use, since both of the joints, they are Revolute joints. So one thing important we need to have is to find out my O. So O, 0, clearly from the previous slides, this is going to be O, 0, O1, and O2. So what we're going to have is O0 going to be 0, 0, 0. O1 is going to be L1 cosine theta 1, L2 sine theta 1, L1 sine theta 1, and 0. O2 is going to be L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2, L1 sine theta 1 plus L2 sine theta 1 plus theta 2. And this is 0. So those are the things we have. You might also notice that those components actually are related to something we have already done. That is, let me change the color so you have a better idea of what I'm talking about. This one, obviously, we know is going to be the origin of the system. This one over here, go back to the previous slides, is actually this one over here. So this is also T0 to 1. We are not looking at this one. We're actually looking at this one. So this is going to be the O1 we have, and that's based on the transformation matrix from frame 0 to frame 1, which means this part over here is going to be related to this transformation matrix, and it's going to be those 3 parts. So keep in mind those are important to us, and we need to use those information to come up with the information of O0, O1, and O2. Once those information are identified, the second thing we want to do is to find out how we're going to generate JV and J omega. Let me change my color back to blue. So join 1, which is Revolute. When we do something like this, my J1, based on the formula, is going to be Z0 O0 sorry. Let me do this one again. My J1 is going to be my Z0 O2 minus O0. You need to be careful about this one. It's always the end one, okay? So in this case, we have 0, 1, and 2. This one is always O2. If you have more links, this one is always at the end, the end position. And we start from, we are dealing with J1, so this is going to be 1 minus 1. So it's going to be O0. That is something we're going to have over here. For the J omega part, it's going to be Z0. So Z0 over here comes from the this part. Okay, so when we are dealing with those kind of things, Z naught is actually from the matrix, the frame, to itself. So A naught, in this case, obviously Y, because we are trying to convert the rotation from itself to itself. So it means that we are not rotating at all, which also implies it's going to be identity. So when you are dealing with zero spring, the transformation matrix is always an identity because you transform yourself into yourself. So it must be identity. With that said, over here, we are having this one minus this one multiplied by this column. So let me change the color again so we have better idea what I'm actually looking for. This one. So when we are dealing with that, I have my Z naught equals to 0, 0, 1. I have my O2 minus O0 equals to this one minus this one. So essentially, it's going to be one sine theta 1 plus L2 sine theta 1 plus theta 2, 0. Okay, so we need to multiply Z naught with O2 minus O naught. And this is going to be cross product. So you have this vector cross product with this vector. So you can use I, J, K, 0, 0, 1 with this one, 0. So if you do that, you're going to find out the result is going to be negative L1 sine theta 1 minus L2 sine theta 1 plus theta 2. This one is going, second component is going to be L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. The third column over here, the third component over here is going to be 0. Let me much better. So this is going to be my JV1. So if we put everything all together, JV1 is going to be negative L1 sine theta 1 plus minus minus L2 sine theta 1 plus theta 2 L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Oh, I'm sorry. This one over here should be a cosine. And third column, third component is going to be 0. Then we need to put this part back here. So it's going to be 0, 0, 1. So this is going to be the 6 components we have for J1. Let's deal with J2. Change my color back to light blue. Okay, So join 2, still Revolute. Okay, so what we're going to do is J2 equals to write down the equation, write down the formula before we move on, because it's easier for us to identify which components is required for this calculation. This is going to be O2 minus O1. This is going to be Z1. So Z1 over here, let's go back to the previous one. So Z1 is going to be this column over here, which is still 0, 0, 1. So just put 0, 0, 1. Keep in mind, this is going to be the transformation matrix of the first frame, and it's going to be 0, 0, 1. And for the O2 minus O1, this one needs to be more careful. This is O2, this one over here. I'm going to minus this one. So what I'm going to have becomes let me use another color so we have better idea what we're talking about. So this one over here is going to be L2 cosine theta 1 plus theta 2, and this one is going to be L2 sine theta 1 plus theta 2, 0. Okay, so now we got all our information over here. So next thing we want to do is to find out what is the 6 components based on the formula we have over here. So we are going to have this one over here. So we have our JV2 equals to ZI cross product O2 minus O1. This one cross product with this one. So I have I, J, K, 0, 0, 1. I have L2 cosine theta 1 plus theta 2. I have L2 sine theta 1 plus theta 2 and 0. So after operating the cross product, we have the 3 components as negative L2 sine theta 1 plus theta 2, L2 cosine theta 1 plus theta 2. The third component over here is still 0. So we get JV2 over here, and we need to put everything all together as our J omega J2 component, J2 column. So that's synthesize everything. So by combining this one and this one, we have our J2 equals to negative L2 sine theta 1 plus theta 2, L2 cosine theta 1 plus theta 2, 0, 0, 0, and 1. So this is going to be my J2. Therefore, my Jacobian J is going to be J1, J2, put them all together, you get your Jacobian matrix becomes this one. L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2, 0, 0, 0, 1. Use another color. We have negative L2 sine theta 1 plus theta 2, negative L2 cosine theta 1 plus theta 2, 0, 0, 0, 1. So, with those information, we successfully come up with my Jacobian matrix. We can use this one to calculate for this matrix multiplied by, in this case, Q1, Q2, or theta 1, theta 2. Dot, of course. Then you should be able to find out what is my current linear velocity and my angular velocity. This is the first example we talked about. And let's take a break, and we're going to talk about the next example.